In this video, we will be talking a little bit more about mathematical induction. Okay, probably one of the first problems a student will be asked to solve when they are taught about mathematical induction is to prove that the following statement, P of n, which is 1 to the power of 2 plus 2 to the power of 2 plus all the way up to n to the power of 2 is equal to n times n plus 1 times 2n plus 1 over 6, and this is true for any n that is a natural number greater than or equal to 1. Okay, so we know that mathematical induction is a way of proving various statements involving natural numbers. So I wrote down the two steps that one would have to check if they want to claim that they have a proof by mathematical induction. So the first step is the verification step, in which case it involves us proving that P of 1 is true. All right. Now P of 1, if we replace n by 1 in this equality, we get 1 to the power of 2 is equal to 1 times 2 times 3 over 6. Okay, it's easy to see that this is a check. All right. Now, the second step is the inductive step. The inductive step goes as follows. So we take some random natural number that's greater than or equal to 1. Okay? And we assume that P of n is true. All right? Now, P of n is this equality. So we now have some power because we assumed that this equality is true for this n that we chose. Okay? And mathematical induction asks us to prove that P of n plus 1 is true. Okay? Well, P of n plus 1, I wrote it down here. P of n plus 1 is 1 to the power of 2 plus 2 to the power of 2 plus all the way up to n plus 1 to the power of 2. I even wrote the term before n plus 1 to the power of 2 is equal to n plus 1 times n plus 2 times 2n plus 3 over 6. And I got this fraction here by going back into our original equality and working on the right hand side of it by replacing n by n plus 1. All right? So how would we go about proving this equality? Well, we can start off with the left hand side of it. So we can say 1 to the power of 2 plus 2 to the power of 2 plus all the way up to n to the power of 2 plus n plus 1 to the power of 2, all right, is equal to. How do we work on it? Well, we can notice that this part of our sum is exactly what's involved in this equality here. All right, so now our assumption is that this sum is equal to n times n plus 1 times 2n plus 1 over 6. So we can use the power that we have by making this assumption. So what we get is n times n plus 1 times 2n plus 1 over 6. And then we copy the last term of this sum, so plus n plus 1 to the power of 2. Right? So our assumption actually allowed us to go from this sum to this sum here. Right? As you can see, that the main difference between the sum that we got now and the sum that we had on the left hand side of this equality is that there are no ellipses anymore, right? So this is a nice way of actually writing down sums, but these ellipses here hide complexity, while this expression here is a closed expression. So what we see is what we have, so it's easy for us to manipulate it. All right, so now all we need to do is show that this sum here is equal to this. All right, so if we can show that this is equal to n plus 1 times n plus 2 times 2n plus 3 divided by 6, okay, then we can claim that by mathematical induction this statement P of n is true for any n that's a natural number. All right, but the equality between this expression and this expression is just a simple matter of algebraic manipulation. Okay, so I leave this for the eager student to check. Okay, this should be of no difficulty checking this. All right, so now we can claim that by mathematical induction, we proved that this statement P of n is true for any n that's a natural number. So we solved the problem. Okay, but before we move on to another problem, let's spend an extra minute on this. What did we actually do? All right, so we proved this equality here. All right, what does that mean? Actually, it means that somebody before us did some work on this sum. All right, and they figured out somehow that the sum is this. So, the real problem here, from the mathematical perspective, is not necessarily checking induction here. The real problem is, how can we prove that this expression, this sum, is equal to this fraction? All right? Or how do we come up with this fraction ourselves? All right? Because that may turn out to be way more important and more difficult than just checking that this equality is true by using mathematical induction. So in the next video, I will show my take on how we can come up with this fraction for this sum here.